So, hello, good morning everyone. My name is Krzysztof Opasiak, or some non-Polish speakers, Krzysztof, Chris is good enough. I'm not used to use hand microphones, so I hope I won't shout too much on you. Today I would like to tell you a few words about our problems with imperfect software. Personally, I think that there is no such thing like perfect software. There is only a software in which developer puts as much effort as is needed to get some kind of certificate like SFO or anything like this. So, what is the schedule for today? First of all, I would like to give you some brief introduction to our problem. Then I will show you how we tried to fix it using the audit subsystem. And then I will discuss POC of rlimit-events, which is a new functionality which we would like to add to the Linux kernel. And in the end, I hope to have some discussion and feedback from you about patches, about the general idea and how we could improve this before sending this to LKML. Okay, so we are all IT guys. We are talking about software all the times. So let's start this talk with talking about something more pleasant. Let's talk about holidays. Holidays, yeah, you also like it. Okay, so let's say that we have a friend. A friend is called George. And George is a really clever guy, but he cannot count money. And each time when he goes to holidays, he takes a suitcase. A suitcase is filled with money on the top and toilet paper in the bottom. And the rule is that if George has enough money on the top, he pays for everything with money. When he runs out of money, he tries to pay with toilet paper. So the question is George going to go to jail on these holidays to which you are going together? Well, it depends. Assuming that owning a toilet paper like this one is legal, but trying to pay with this is illegal, then if George tries to pay with toilet paper and get caught, he will go to jail. If he won't get caught, or he doesn't pay with toilet paper, he won't go to jail. So what we can do to help George to not go to jail? First of all, you may teach George how to count money. This is the perfect solution because it's going to work not only for these holidays, but for all holidays in the future. So it's the best and the most preferred way, but it's not always possible. Let's say that we cannot do this. So what else we can do? First of all, we may try to check George's suitcase every n minutes. But the problem here is that we have to choose the value n, which we don't know how big it should be. It keeps us busy for all the time because every, let's say, 10 minutes we have to check, George, show me your suitcase. So show me your suitcase. How much money do you have in it? So it's, let's say, possible, but not perfect. Another solution is to install some kind of IoT hardware in the suitcase, which will notify us when there is X money left. Let's say that X is the value that George needs to get back to home. So when we get such notification, we can go to George and say, my friend, it's time to go home and refill your suitcase. In real world, we use money as resources. But let's go back to the software and to Linux. In Linux, we have generally two types of resources. First of them are system-wide. It means that they are shared between multiple processes. It's like CPU, because we have limited CPU time, it's the memory, I/O, and many other resources. For most of them, we've got C groups, which can be used to control, or even some of those C groups, like memory C group, may be used to get notification about the usage. On the other hand, we have process-specific resources. Those are resources which refer only to one process, like CPU time. As you see, the CPU time is here and here, because you may limit the CPU time for a group of processes and for one particular process. We have the stack size, which is private for every process, number of open file descriptors, etc. Most of these resources is controlled using the error limits. If you'd like to know all the limits, just man set error limit, and you will get more info. So let's try to code George behavior in C. We have a simple function which just opens the path and write the data to that file descriptor. What are the problems here? First of all, we don't check the return value, and the second one, we are not closing the file descriptor. So, is this function going to work? Yes, as long as path is valid, and as long as we won't reach the number or the limit of open file descriptors. So in perfect environment, when we don't have limits, this is going to work. But if we have limit for number of open file descriptor, this function is going to lose the data silently. So what we can do? The perfect solution is the same as with George. Just go there and fix your bug. It's your bug, this function is wrong and shouldn't look like this. You should always check the return value, and you should always close the file descriptor after usage. So that's the perfect solution. But what we can do if we don't have the source code? If we are running the binary blobs, if we are running some proprietary libraries, if we are running some other proprietary source, and we cannot do anything with this. So we can try to use some monitoring solutions. Who is working here with servers? No one? Okay, so who knows what Nagios is? Also no one. Okay, so Nagios is a software for monitoring server farms. You can monitor the resource usage, the number of running processes, CPU, memory usage, and basic, let's say, how it works is that every n minutes it checks the resource usage. So every 10 minutes you check the memory usage, every 10 minutes you check the CPU usage, etc. So you have no idea what happens between those checks, but you've got this check in a given point in time. It's classical point on the resource usage. It's good for servers because usually your server is connected to some power plant and you've got almost unlimited power. You're just going to get a bigger bill. But if you are trying to do this for small IoT devices, power consumption and waking up the platform every 10 minutes, every 1 minute, or it depends on the interval of your check, this starts to become a problem. Moreover, we have no idea what happens between checks. And we notice that in IoT world, we have a long periods when nothing is happening, and then the user comes back to home and it starts, okay, so now turn on lights here, to turn on lights here. So you cannot, let's say, predict where the usage is going to be. So another solution is to get the notification from kernel when level is reached, or even better, to get the notification before the limit which is enforced for the process is reached. So for those of you who doesn't know, the error limits are forced in a resource-specific way. It means that, for example, for a limit of open file descriptor, if you get to the limit, you will get the minus EM file error from the open. If you reach the limit of CPU, you will just get CQ. If you reach any other level, you will get the resource-specific notification. There is no generic mechanism to get the notification that you crossed the limit. So what we tried to do is to use kernel audit subsystem to get notification about reaching limits. How does it work? We tried this for limit of open files, and we tried to trace the moment when open returned the EM file value. So we just set the error limit to some reasonable value. For example, for simple application, 200 open files should be perfectly enough. And then you use audit syscall, so install a filter to get notification when audit syscall, when open syscall returns the EM file. What are the problems with this solution? To be honest, this works. It's fine, it works, but there are a couple of problems. First of all, we get only the post-factum notification. It means that process already received this error. If there is a bug in error path, if there is a piece of code like this one on the previous slide when you are trying to write the data without checking the return value, this data is going to be lost. You cannot do anything with this. Error is returned to the service, so if there is a bug like null pointer the reference in the error path, you are going to trigger this. Moreover, not resources are traceable. For example, CPU usage does not depend on a syscall, so it's hard to trace it if you trace only syscalls. And the last and a very big problem is slow. Audit is really slow. To trace only the open, so you install only single filter for open syscall and for one return value, there is an overhead of 33% for opening code file. I mean, by code file, I mean the file which is not cached previously, which is read from the disk. And for hot file, or for file which is on TMPFS, you get 45% of overhead. It means that your system is running almost 50% slower than without monitoring using audit. So that's why we are trying to develop alternative solution which will give us a notification about resource usage without such overhead. So this is where rlimit-events comes. And this is the notification sent by kernel when given process crosses the certain resource usage level. For example, if you install the filter for 10 open file descriptors, you will get the notification when process crosses from 9 to 10, and then when process crosses from 10 to 9. So every time you cross the line, you get the notification. So resources are the same like in error limits, because this is process specific. Notification is sent via file descriptors, because if you do this in using file descriptor, you will get the automatic cleanup. When you close the file descriptor, you don't need to handle the process lifecycle like you have to do with audit. And monitoring level can be smaller than the actual limit set for that resource. It means that you may set the error limit for, let's say, 100 file descriptor, and the notification level for half of this. It means that after you get the notification, you still have the time to do something with that service before it will lose the data. A little bit similar concept, just for your information, has been submitted a year ago or even more to LKML, but it has been rejected due to trace point usage. There was a comment from the community that trace points as kernel API are not acceptable, so they rejected the patch and the author didn't send any fix or anything like this. That's why we took up this. So the API. To be honest, I really don't like this part, but I didn't came up with anything more clever. So to get the notification file descriptor, which is used to monitor, you have to send message via netlink, and then you receive a brand new file descriptor, and you may install some notification level for specific PID and for the resource and the level you'd like to monitor. You use this, you install this using IOCL, and then you may simply read on that file descriptor, or you use poll to get the notification. Inside the notification, you will get the information about the PID of process which crosses crossed the resource and the new level. Because our limits are inherited by all the children, by default the notification levels are also inherited. It means that if process is forked, then you will get, using this file descriptor, you will get the notification about this process and all its children. So the design inside the kernel. On the left side, you have structures connected with the process. Multiple task structs point to the same signal struct, which is shared between all tasks in the process. Here we've got the struct file, which is connected to the monitoring file descriptor. So this is the monitoring side, and this is the subject side. This is the context of watchers, and watcher is the information about the level when you need to send the notification to the user space. So every watcher resides on two lists. One of them is inside signal struct, and the second one is inside watcher. When you add new level, you add it here and here. Every time when resource is allocated, you iterate over this list and check if you have to trigger some watch. What are the benefits? First of all, if you compare this to audit, you don't need to do any kind of filtering in the user space. With audit design, you've got a single audit daemon which resides in the user space, and then it has to route the communication to different plugins. Well, the problem is that you have to wake up the audit daemon, pass the message, then use another form of IPC to pass the message to another daemon, then you have to wake up another daemon and check the usage. And then it may turn out that, for example, you are not interested in this particular process, or you are not interested in this particular resource. So you have to do all the filtering in the user space. It's not so easy to create a suitable audit filter which will be inherited by process children. Nextly, you can have multiple monitors. You can have only one audit daemon, which will get all the messages about whole system. And here, you may have multiple monitors, which monitor only part of the system. So for example, you may say that now I'm monitoring only those two processes, and another instance is monitoring another 3 processes, or anything like this. Multiple levels of notifications are allowed. So not only the EM file, the moment of reaching the limit, but also multiple steps in between. We can prevent the data loss. So we can catch situations like on the previous slides. So we can do something, because usually if you have some proprietary service, it's able to be restarted cleanly, but it's not able to handle its own bugs. So when it reaches the limit, you may send the signal, the sig user or sig term, and restart it to free the process-specific resources. In addition, Nagios, the monitoring system which I mentioned, has the possibility to install passive checks. And passive check is a kind of check where you don't run the scheduler with the polling. You just simply wait for the messages. So for example, instead running every 10 minutes a check for the number of open file descriptor. You may create a plugin which will just send a notification when particular level is reached. Not to mention that most of Nagios uses is just simply run the check every 10 minutes and then do something if the check is, let's say, 5 or 10. So it's almost the same functionality. There is no free lunch. It's not free. Error limit events are not free, but are relatively cheap if you compare them to audits. The measured overhead is, if there is no watchers, there is only 1% or even less. And for a single watcher, there is 5% overhead for hot file and only 1.6% overhead for cold file. So if you compare this to audit, where you had 2-digit results, then it's really, really cheap. So the current state is POC ready. I'm going to send this, let's say, in next 2 weeks to the LKML after I fix all the, let's say, hacks and implement pool. Maybe I will try to implement this for other resources, not only for file descriptors. And I want to send this as soon as possible to get feedback. And this is also the goal of this presentation, to collect feedback from you. Because personally, for example, I hate this solution with Netlink to get this, but I didn't come up with something more clever, because using ProcFS is not so easy to open to get special kind of file descriptor. It's not the way you should use the ProcFS. So if not ProcFS, then what? A virtual device, it also doesn't make any sense. So now it's time for discussion. If you have any comments, any ideas, generally is the idea fine? Does it look to be acceptable in upstream? Is the API fine? Maybe we may think about something better than Netlink to get this notification file descriptor. And the last question is the security. What permissions should be necessary to install watch for particular process? Do you have to be root, or you have to have access rights, or you need to have some specific capabilities? What do you think? What's your opinion on those? I'm open for any comments.
Hi. For your last question, I think it should be user, no need to restrict it to root, and capability is a good idea. And for the API, my question is, why you use IOCTL? Since you started with read, why you don't use write to send the structure to the Netlink interface?
Well, I didn't want to use write. I left it, let's say, for a future. Because if you would like to make this interface, let's say, more flexible, I think the IOSQL is the better way to make it more flexible. Now we are using, it's not right. If you are using read to get the notification, then write, which is the opposite information, for installing filters or for removing filters, it's, I think, more obvious it's to use the IOSQL. You have at least 2 types of messages you want to send. Install a new notification level or remove the notification level. So, you know, that's, let's say, using write for this, if you use read to get, okay, the resource has been reached. And using write, okay, I would like to monitor this resource. Let's say, I thought that using IOSQL would be more obvious. I saw a lot of usage of IOSQL in this way, so that's why I also use it.
Maybe this is a kernel developer point of view and not a user level point of view. It's easier when you are a user to implement read, write, and then use it, use the API.
Okay. Okay, thank you. I will try to consider it. Any more comments? Some kernel developers here? Does the idea itself looks fine, or are there some obvious bugs which I don't see?
My question is,
so who are we going to submit this to, I guess, is the question. Who's the maintainer? Who you're...
I didn't check, because it's, let's say, the problem with error limits is that every subsystem, every limit holds the value on its own.
Right.
So the work is split between many different subsystems.
Yeah, I don't call myself a kernel developer, but I have developed for the kernel in the past, and these types of patches that cover lots of subsystems, they're notoriously difficult to get upstreamed.
Yes,
just
I know.
because you got to get a bunch of people on the same page, and a lot of times people, well, anyway, it's like a tangential to their main work, right? The subsystem work, so you don't get as much attention as would be good. Anyway, that's just a caveat. I don't have any solutions for you.
Yeah, I know. That's why I'm doing this presentation, because it's gonna be hard to get this inside the kernel. There are a couple of obvious problems, like for example, for number of open file descriptors, there is simply no counting of such thing like number of open file descriptors. There is just the bitmap, and there is no function get number. And you cannot simply write such a function because there is no locking for this bitmap. It just, every operation is atomic, and you don't have any spin lock or anything like this. So there are a couple of major changes in different subsystems, and it's gonna be really hard and painful to get this. Any more comments, questions? Okay, so thank you for your attention. If you're interested, then the code is on my GitHub, also the tests, the Userspace application. Feel free to grab it, to send me some comments, send me an email. Thank you.